Hey everybody, it's Mr. N, and here is an additional review for the Semester 1 final. This review has 3 questions, so you can scroll through if you want to see what the other 2 questions are besides this first one. So let's just go ahead and get started. All right, for problem number 1, this is a no calculator allowed. It says the figure shows a graph of f prime, so this is f prime, the derivative of the function f, on the closed interval from negative 9 to 9. The graph of f prime has tangent lines at x equals negative 6, so we've got a tangent line right there. X equals 2.5, so we have a tangent line right there. So those are tangent lines as indicated, and then another one at 6 here. So this is definitely a kink in the f prime graph there and right there. All right, so then part A says, for what values of x is the graph of f increasing and decreasing? Okay, so this is f prime, remember that, so we need to determine what parts of f are increasing and decreasing. And for part B, concave up and concave down. Okay, so I know they're going to ask these 2 questions, so I'm going to go ahead and do one thing right away that'll help me out. So I'll be putting a number line in right under it. We'll do that, like that. And then we'll do another one right under it right here. And this one will be for f double prime, and this red one will be for f prime. So what I'm going to do now is for the values of x that are increasing and decreasing, I'm looking at part A over here. What I'm looking for is for increasing, I want f prime to be greater than 0, and for decreasing, I need f prime to be less than 0. Okay, so here is my number line for f prime, and I'm reading this off the graph. So for it to be right here above the axes, that means I have a positive f prime. So I have a positive f prime up to negative 8. So up to negative 8 right here, I have a positive f prime. And then it goes below the axes on this part right here. So all this is negative f prime up to negative 4. So this is negative 4, and I have negative f prime. I'm going to continue this process. So all the way to negative 1 right here, these will be positives. And then over here, all the way to 1, these will stay as negatives. And then again, I go above the axes to 4, so these are positives. And then I go back down below the axes till 8 right here. So I will be below the axes, and then I'm back above the axes. So that indicates where my f prime is positive and negative. So that means for increasing, I'm looking where it's greater than 0, so I'm looking for positive. So that's going to happen on these intervals. So negative 9 to negative 8, union. The next one will be right here where it's positive from negative 4 to negative 1. So negative 4 to negative 1, union. Then the next one, if you take a look, will occur from 1 to 4. And then the last one will occur from 8 to 9. Okay, so we've got all these 1 to 4, 8 to 9. For decreasing, I'm going to take a look at when it's negative. So from negative 8 to negative 4, that's negative, and then we've got another one from negative 1 to 1, and then another one from 4 to 8. So let's write all these down. So we said we had one from negative 8 to negative 4, union another from 0 to 1, union 4 to 8. Again, just to recap this, I took a look at my graph where it was above the axis or below the axis. That tells me if f prime was greater than 0 or less than 0. I put it on a number line because it's easier just to see it on here. Well, you could see it here. This is above the axis, below the axis, but this clarifies it. Also, it's going to probably help me later on in the next set of questions. Okay, for concavity, I'm going to do something similar. So for concave up, what we want to do is we want to determine when f double prime is greater than 0, and for down, we need f double prime to be less than 0. So I'm going to do something similar. I'm going to go back to my number line over here, and I'm going to determine where this is greater than 0 on the second derivative or less than 0. So since I'm looking at the second derivative, I'm looking at the derivative of f prime, so I want the slopes. So these slopes all are negative right here. These are all negative, then it gets to be a horizontal slope right here, right? These are horizontal tangents, and then it turns to be positive again. Okay, so right here, negative slope turns to be positive, negative slope turns to be positive tangent slopes. Remember, I'm looking at the tangent lines, so these are all tangent lines right here. Let me change my pointer so you could see if I draw it as a tangent like that. Okay, tangent like that would be negative, tangent like that on this side would be positive. So let's go ahead and indicate those intervals. So we said up to -6 right here, and this would be negatives. Over here, from -6 to -3 would be positives. And then over here we have negatives again, all the way to 0. And then from 0 we turn positive all the way to, this is 2.5. Okay, then we turn negative again. These are negatives all the way to 6 right here, which becomes, after 6, these slopes all become positive slopes all the way to the end. So now I'm going to slide this up a little bit, and I'm going to take a look at the number line. You can look at the graph again, that's fine. You can look at the graph to determine these intervals, but I do the number line just because it's easier for me to see it right away, and again, it'll help me later on in these problems. So it's concave from -9 to -6, and I'll just go in order right now. From -9 to -6, it's concave down. Then the next one from -6 to -3, it's concave up. And then the next one from -3 to 0, that's going to be concave down, so union -3 to 0 under the down part. Then from 0 to 2.5, that's going to be up, so let's put it up here. From 0 to 2.5, and then from 2.5 to 6, we got concave down again, so that's 2.5 to 6. And then from 6 on, it is concave up, so we'll put it right here, from 6 to 9. All right, for now, the next question. It is asking us to determine where we have a local maximum or local minimums. So local maximums and local minimums occur whenever this changes from increasing to decreasing or decreasing to increasing. So right here we're changing. We're going from positive slope on the original to a negative, so that's going to give me a relative maximum. This is negative to positive. Let me write it so you can kind of see it a little bit. So this goes from positive slope on the original to a negative. That's going to give me a maximum, negative to positive, and so on. So let's go ahead and indicate where we're going to get relative maximums and relative minimums. So f prime will say changes from, this is the reasoning, from positive to negative, thus local maximums are going to occur, and this happens at x equals, this is at -8, this also happens at -1 and at 4. And in a similar pattern, f prime changes from negative to positive, thus local minimum, and this will happen at, over here from negative to positive, we said the first one's at -4, then the next one, taking a look, happens at 1, and the next one happens at 8. All right, so now we have to find the x-coordinate of each point of inflection for f and justify your answer. Okay, so point of inflection are possible points of inflection. We'll say possible points of inflection is when f double prime equals 0 or undefined. All right, so we're going to take a look at f double prime. And that means 0 happens at horizontal tangent at -6. Undefined is at 3 right there because it's a kink, right? 0, 2.5, and 6. So these are all the points we need to test. So we need to test x equals -6, -3, 0, 2.5, and 8. Or sorry, 6. Well, guess what? In this particular problem, every single one of these changes from a negative to a positive. positive to a negative. So it changes sign at every single one of these. So since they all change sign, since all change sign for f double prime, all are points of inflection. So all of these end up working, so every single one of these is a point of inflection. Okay, next I need to determine where the graph is concave up and has a negative slope. So we're looking for this. We are looking for concave up, negative slope. All right, so here's what I'm going to do. I'm going to go back to my original number line over here, and I'm going to do something. I'm going to compare the intervals. If you take a look, I can go like this, I can go like this. I'm breaking this up into like segment parts, and I'm going to take a look. Here's -1, there's a 0, then we've got 1, and then we've got 2.5. Right here are all my little areas, and I am looking for where it's concave up. So to me, this tells me that f double prime is greater than 0, and negative slope, which means f prime is less than 0. I'm looking for the intervals where this occurs. So I want f double prime to be greater than 0, so this happens right here, but then I need f prime to be less than 0, so right here. So this interval between 6 and negative 6 and -4. And then it happens again between 0 and 1. Right here I have a positive f double prime and a negative f prime. And then it happens again between 6 and 8 right there. So let's write all these down. So we said this occurs, thus, I'm looking for that to happen. So thus, this occurs at the intervals from -6 to -4, union 0 to 1, union 6 to 8. All right, that's a negative there. There we go. And those are the reasons why. Because f double prime is greater than 0, f prime is less than 0. All right, let's move on and take a look at what the last one has us doing. And now we are going to sketch a possible curve of f on this graph. Okay, so the first thing I want to do is start with the point they gave me. So start with, they told me that f of -3 equals -1. So I'm going to go -1, 2, 3, -1, and I'll put a point right there. Next, they say there are horizontal tangents. So next we have horizontal tangents, and this is where f prime had equaled 0, right? And or had changed from positive to negative, increasing, decreasing, or undefined, right? We're going to do that. So these occurred at x equals -8, -1, 4, because these were maximums. And then we said -4, 1, and 8, which were our minimums. So moving up here, just to show you where I got this from, right here is our local maximums and local minimums. So I'm going to use those to help me graph this. So I'm going to go through, and at these points, I'm going to put horizontal tangents. So we'll start with -8, and I'm just going to go like this. Just lightly go like this to let me know that the original graph flattens out right there. And then I will do the same thing at -1. So I know that the original graph flattens out right there. Then I will do that at 4 right here. I don't know where it's, how high up or how low it goes yet. I don't know that yet. Okay, then let's do the minimums at -4. We're going to have a minimum, so it will flatten out on the f original graph. And then at 1. And then another one occurs at 8. 6, 7, 8 right here. So it will flatten out and reach a minimum. All right, now it's a matter of taking a look at the concavity and if it's increasing or decreasing. So I can use the number line that I created right here to help me. So I'm looking at the intervals where it's concave down. So from -9 to -6, it's concave down, but then it's increasing, so the slopes are positive from -9 to -8. So concave down and positive, that would give me something that looks like this. Now, how high up or how low I go, so it'll be, I'm just going to put it up here, okay? Then I know in the next interval, it's concave down, and then it reaches a minimum right here, but then comes back up through that point. So this has got to be concave down, and then there's an inflection point over here. There is an inflection point at -6. So somewhere right here at -6, it's going to change concavity. So this is concave down, and then it goes concave up, like that. My curve doesn't look so smooth. And then we're going to continue this whole same cycle. Then we've got a concave up, and then we hit the inflection point, and it goes down. And then you can come back down over here. You can go as low as you want. But notice I also went through this point right here. You can go as low as you want. We don't know how high up or how low to go from this. So these are just an approximate. So you can go all the way down. You could just go to here. And then basically it's going to go back up, and then it's going to go back down. There's a point of inflection right there. And then you can come down to here. You can go through here. It doesn't matter. So I will finish this up now, and let's do this. So we said it's going to come right down through here. I'll just go to here. That's okay. And then it reaches a maximum. So we'll get my curve kind of smooth. It reaches a maximum. Then we have a point of inflection at 6, somewhere right here. So I'll change concavity. We'll say it's right there. And then we'll just go like that. I didn't hit the minimum so good, but that's okay. But you get the idea. So that's what it looks like on -9 to 9. And notice I didn't put arrowheads because we're only doing it from -9 to 9. All right. Let's move on to the next problem. So suppose we had this curve. We need to find dy dx, then we need to find it at this point, then write the equation of tangent line at that point, and then you know what, we are not going to do this one. We're going to skip this one. This one's a little bit too difficult, and you won't get anything that hard on the AP test. So we'll skip that one. So let's take a look at this first one and see what we got. So it's saying that we have to find dy dx for this curve. So let's go ahead and do that. So what I'm going to do is I'm going to do implicit differentiation. And so this becomes, over here, working on this one, this will be 3x squared dx over dx, so we don't write it. And then we're going to say, here I'll break this up into -3x squared and then a y. So we're going to need a product rule. So so this will be negative first times derivative of the second. So that'll be -3x squared times dy dx. And I'm going to write my dy dx in this problem as y prime. Okay, so times y prime. Okay, then so first times the derivative of the second plus the second, which is y, times the derivative of the first, which will give me -6x dx over dx, so I don't write it. Okay, now let's do plus. Now let's do the derivative of this one. So again, I'm going to need the product rule. So this will be first times the derivative of the second, so that'll be times 2y y prime plus the second, which is y squared, times the derivative of the first, which is 2. And then I need to take the derivative of this one, which is 0. So let's clean this up a little bit. I'll end up with 3x squared minus 3x squared y prime minus 6xy plus 4x y prime plus 2y squared equals 0. And then I will go ahead and see what I could do as far as putting the y primes together. So this becomes -3x squared y prime plus 4xy y prime, and then bring the others over to the other side. So that'll give me -3x squared plus 6xy minus the 2y squared. And now Continuing on with this, I will take the y prime out. I'm going to just do this all in one step. I'm going to take the y prime out and then divide it over. So I will get y prime, which is my dy dx, as being negative 3x squared plus 6xy minus 2y squared all over negative 3x squared plus 4xy. And just to address that running water in the background, that's the fish tank. It's supposed to be tranquil, but it's kind of loud. All right, so for part B, we do have the dy dx, which is our slope, and we just have to plug in this point. So dy dx at this point will be negative 3 times negative 1 squared plus the 6 times negative 1 times 3 minus 2 times 3 squared, all divided by negative 3 times negative 1 squared plus 4 times negative 1 times 3. And this will give me negative 3 minus 18 minus another 18 over here. And on the bottom, I'll get negative 3. And then this will be minus 12, which will give me negative 39 over negative 15, which can reduce down to 13 over 5. All right, so now for part C, we need to find the equation of the tangent line, which is the same process. We need to find dy dx because this is the slope, and we did this in part A, but we want it at this point. So I need to find the slope at that point, so I'm going to plug in 2 for x and negative 1 for y into my tangent line, or my dy dx equation that I had already solved for. So let's go ahead and do that. So I'll have negative 3 times 2 squared times plus 6 times the x, which is 2 times the y, negative 1, minus 2 times negative 1 squared. On the bottom, I will end up with negative 3 times 2 squared plus 4 times 2 times negative 1. Okay, cleaning this up, I'll get negative 12 minus 12 minus 2 all over negative 12 minus the 8, which gives me negative 26 over negative 20, which reduces down to 13 over 10. All right, so this is my slope. So I go y minus y1 equals m times x minus x1. There's my point slope equation. So y minus negative 1, so this will be y plus 1, equals the slope, which is 13 tenths, and then x minus the 2. So there is my tangent line. All right, let's move on to the next question. And this one is a calculator allowed question. And it says, the position of a particle moving in a straight line is given by this equation, where t is in seconds. Now notice it says f of t equals this. You are used to using, for position, you are used to seeing it as s of t or even x of t. Usually on the AP test, they will put it as x of t. But that's okay, it could be an f of t. And t is in seconds. So find the average velocity of the particle over the interval from 0 to 4. So my suggestion for you on this problem is to go ahead and put it in your graphing calculator. Put y1 as this equation, okay? y1 equals that equation. Then you're going to say y2, and it's going to be n derivative of y1, right? We're going to do that in our calculators. And it looks like when we have to determine, if we look ahead, it says speeding up, slowing down. We're going to need the y2 in our situation here to be n derivative, or y3, sorry, n derivative of y2. And let's clarify why. Over here, this is the position graph. This derivative of the position is going to give me my velocity, and this is going to give me my acceleration. Now, I'm saying put it in your calculator because it's calculator allowed, and this is going to be pretty tough to do without a calculator. Now, for part 1, it says average velocity. Well, average velocity is the change in position over the change in time. So in this case, it's going to be delta f over delta t, and I have, this will be f of 4 minus f of 0 over the 4 minus 0. So I can go ahead and use my calculator, plug these in. So take f of 0. In fact, you can even just put it in here first and then choose the value and find it at 4, and that'll give you 52. At 0, you will get 0 over 4, which gives me 13 units per second as my average velocity. Remember, there's a difference between average and instantaneous. Average is the change in position over the change in time because it happens on an interval. If I wanted instantaneous, if I wanted to know my velocity at 2.5, well, that would mean take the derivative, which would give you the velocity equation, right? And then plug in 2.5. So there is a difference there. All right, now for part B, it says determine the intervals when the particle is moving left or right. So left or right means I need to determine when the velocity is positive or when the velocity is negative. So I'm going to go ahead and graph all 3 of these on my graphing calculator, and I'll put it here for you. Okay, so here's my graph for the velocity, for the position, the velocity, and the acceleration. This green one right here is going to be f of t. This red one right here will be v of t, so that is the derivative, as I had indicated to put it right here, and derivative of y1. And then this bluish one right there is going to be the second derivative, which will be a of t, just so that we can clarify. Okay, to solve this, we need v of t, and when v is less than 0, this is moving to the left, and when v is greater than 0, this is moving to the right. So let's try to find out when this is happening. And I will put these on a number line. It will make it a little bit easier. So there's 0 where we're starting off, and I am taking a look at the velocity, which is this red one, and look, I can second calculate on my graphing calculator to find out this intercept, to find out when the velocity is, this is below the axis, this is above the axis, what that point is. And it does come out to be 1. So this does come out to be 1. And I use second calculate, and I'm using the y2 equation, and I want to find the 0, the root. So that happens at 1, so then I know to the left of it it's negative, to the right of it it's positive. So that means it's going left, so left on the interval from 0 to 1, and right will be on the interval from 1 to infinity, because in this question it didn't say up to it didn't give us the interval to 4 like it did in the other one, so we're just going to say to infinity. All right, so there we go, left and right. Okay, so for the next part of the question, let's move all this up. It says determine the intervals where the particle is speeding up or slowing down. I'll move this whole graph up too a little bit so we can see the question. Okay, so we need to know where it's speeding up and slowing down. Okay, so here's what we need. We need f double prime. So f double prime gives me the acceleration. This gives me a of t. Now, and we have to compare to v of t. If speeding up, that means a of t and v of t have the same sign. Slowing down, that would mean a of t and v of t have opposite signs. So again, I'm going to do my number line method, and I'm going to compare these on a number line. This is going to be my v of t, and we already know v of t, this is at 0 here at 1. These are going to be negatives, and these will be positives. Now I need to do the same thing, put a of t right underneath it, and if we take a look at the a of t graph. This is the a of t graph. Notice it's always above the axes. It does not go below from starting at 0. We're not going to go time negative, but from here 0, it is always above the axes. So these are all positives right in here, and now we know, well, right here in this region, we've got opposite signs, and in this region we have the same sign, so let's write that down. So that means it's speeding up when they are the same side, so this is from 1 to infinity, and slowing down, we will say this happens from 0 to 1 because they are opposite signs. All right, so hopefully that was a good little review for you. Make sure you know how to do these problems. These are good classic problems. This is some of the biggest concepts we've talked about in semester 1. There are others, but these are 3 good examples. All right, thanks for watching. Hit that like button and make sure you subscribe to my channel. Hit the notification button so you know when I post up those videos.